We will start with the velocity method, and the first step in the velocity method is to select suitable velocities in the main and branch ducts. That is, it requires some experience for the selection of these velocities. However, when we do a problem based on this method, we will be given these velocities, and that is the starting point. Once we have got the velocities, we will also have been given the volume flow rates, and if you know the velocity and the volume flow rate, you can easily calculate the cross-sectional area of the duct, and if it's a circular duct, then you can calculate the duct diameter. And for rectangular ducts, if you know the aspect ratio, then you can find out the dimensions, or if you know the aspect ratio, you can work out the length of the two sides of the rectangular duct. That is the sizing part. You will get that value, and we will move on to the next step. That is, we need to find out the pressure drop in each of the runs of the duct layout. Because we have already selected the suitable velocities in the main and branch ducts, and we have got the duct dimensions and the volume flow rate, we can use, for example, the volume flow rate and velocity to find out the pressure drop per unit length in each of the main and branch ducts. The next thing will be to calculate the pressure loss for the run that we are working with, and that will include the frictional loss and the dynamic losses. So we add them together, we get the total pressure loss for one particular run. Then you move on to the next run, and similarly you can repeat the process until you have got the pressure drop for all the runs in the given layout. And then you will be able to identify the index run. Once you have the index run, that is the value that will help you select a suitable fan that provides the necessary pressure for the air to be transported to the various exits in the layout. When the index run has been identified, the damper that will be installed in that run will be fully open. But for other runs, we need to have dampers which are partially open, so that the pressure drop that we require at the exit is properly achieved, and that will allow the required flow rate to be diffused through those outlets. This type of a duct design method, that is the velocity method, is one of the simplest ways, and it is used for both supply and return air duct design. As I mentioned earlier, it requires experience, and one of the disadvantages is that the partial closing of all the dampers except the one in the index run is required, and sometimes this leads to what we call unbalanced design. That means some of the dampers are closed to a high degree, some are very sort of minimally closed, rather than having a more uniform position of the dampers in the layout. Okay, if we go back to that layout that was shown to you earlier, and in that, if let's say the run ACGH is the index run with a total pressure drop of 100 pascals, and the pressure drop in the shortest run, that is run AB, is 10 pascals. That means we need to provide an additional 90 pascals of pressure drop by dampering, that is by partially closing the damper such that it provides an additional 90 pascals of pressure drop. That is what is known as dampering. And similarly, we will have to partially close dampers in other runs according to the pressure drop in that run. For example, a run has a pressure drop of 35 pascals, so that means 65 pascals of dampering will be required for that particular run. We now move to the second method, that is the equal friction method. And as the name suggests, the principal requirement for this method is that the pressure drop per unit length remains the same throughout the duct layout, compared to the velocity method, in which the pressure drop per unit length will vary in various parts of the layout. This will have the same pressure drop in all parts of the ducting system. And again, we start with a suitable value for the frictional pressure drop per unit length. And as it was stated earlier, that typically the pressure drops in HVAC ducting systems are within the range of 0.6 to around 5 pascals per meter. But here again, a more experienced designer would be able to provide a more suitable value for a ducting system that has to be designed. However, when we work with a numerical, we will be provided with the pressure drop value that will be used to design the ducting system. So once we have this, it means that the value of delta P by L will remain the same all over the layout. And what it means in terms of the use of the friction chart is that we will have a horizontal line all through. I will go to the friction chart and just show you what it means when we solve a problem using this equal friction method. So I will go to the friction chart, and let's say we are given that the pressure drop per unit length is 0.7. So all we have to do is to just draw a horizontal line like this, and we know that we will always be working on this horizontal line if you are using the equal friction method. Whereas in the velocity method, for different sections of the duct layout, you will have different values of the pressure drop per unit length. And again, we have the two objectives, that we need to find out the duct sizes and then the pressure drop for the various runs, identify the index run against which the fan will be selected, and then we will know how much dampering is required in the other runs. So because the value for the pressure drop per unit length is already set, we can multiply it by the length of the straight part of the run to get the friction losses, and then we will find out the dynamic losses, add them together and get the total pressure drop, and proceed as before to find out the index run, etc. Okay. Now if we look at this method and compare it with the velocity method, this is probably gives you a better design, and of the two conventional methods that is still quite widely used. And when we say it's a better design, that means it gives you more balanced duct sizes and pressure drops. For relatively small to medium ducting systems, this gives you a good duct design. But when we talk about very large duct layouts, it requires a more sophisticated approach in which we might adopt more than one duct design method in various parts of the entire layout. So you can have a combination of the static regain method and the equal friction method, both used together to refine the duct design. Partial closure of the dampers will still be required, but what we expect that it will give you a more balanced partial closure of dampers in the various runs of the layout. One of course problem could arise that if the ducts are very long, then because we have fixed the pressure drop per unit length, we can end up with a high total pressure drop, and because the pressure drop is high, the fan that we will select will have a high static pressure rise, and the ducts near the fan get over pressurized. So that could be one of the things that you have to again keep in mind.